Good afternoon, all. In this particular lecture, we will start with the feature selection. In previous classes, we discussed feature extraction, how statistical methods and principal component analysis is used to extract the feature from the given data. Now, for a given data set, we can extract a lot of features. But the important question is, all features are equally important. If not, then which feature we should select in order to make some decision. So, in this regard, in this particular lecture, we will be discussing ranking, the basics of decision tree, especially the entropy reduction and information gain. Once you understood the concept of entropy reduction and information gain, then you can start working with decision trees. So, what is ranking? So, variable ranking is the process of ordering the features by the value of some scoring function which usually measures the feature relevance. For example, if we conduct the exam of artificial intelligence and machine learning and we arrange their marks in the descending order. So suppose one student received 99 marks out of 100 and is the rank 1. Second student received 97 marks, so he is at rank 2, and so on. Similarly, the rank will be given to other student. So from this particular table, what you can understand that the rank 1, 2, 3, these are the toppers in artificial and intelligence and machine learning score. So what you simply did, you simply organize the scores made by the student in descending order, and the students who received very good marks, you gave the ranks. So if there is a criteria that if a student receive marks greater than 75, then we can say that all these students are in distinction. Similarly, those who receive the marks between 60 and 75, we can call it them as a first class student, and so on. So this is one approach to rank the students according to their scores in a subject. Similarly, there could be several parameters. Based on that, we can rank the features, right? So that is the approach we use for ranking. Now, the resulting set. So the resulting score is generally denoted by SFI, and it is computed from the training data measuring some criteria of feature Fi. By convention, a high score is indicative for relevant feature. So the students who received marks more than 75, they will be in distinction. So the marks is a criteria to decide whether student will be in distinction or is we will be in first class or second class or a fail state. So highest score means more relevant feature, lowest score means irrelevant feature. So accordingly we do it. Again, if we want to measure the overall performance of a student, then what we do? First of all, we can rank students according to their performance in the academics, rank 1, rank 2, and so on. Then we can take another criteria as a sports. Based on that, we can give the scores to each student. Similarly, how he participate in various events. Based on that, again, we can rank the student. And for each student, if we start adding their performance in academics, sports, participation in various activities and other active parameters, then whatever sum will be there, that will be the resultant score of that student. and the student with maximum score or highest score will be called as topper, or is very good student in the class, and the student who will receive the least mark, we can call him as the worst performer in the class. So the same approach we used in ranking. Again, the important thing is that what parameters you consider. These parameters play an important role. So in order to rank the features, we can use either correlation or we can use information theoretic criteria. So many a times we heard about the word correlation coefficient, and this is the particular or typical formula for estimating Pearson correlation coefficient. And we know that based on the value of R, we decide how strongly the two variables are correlated. For example, in first figure you can see there are two variables. First one is X, second one is Y. And the data points are plotted on the X-axis and Y-axis. And here you can see a straight line is observed. And for that the value of R is 1. So we can say that the variable X and Y are strongly correlated. Similarly, in second figure you can see again two variables X and Y. The data points are plotted and we received the value of R as 0.5. So we can say that they are moderately correlated. In third figure you can see that the data is scattered and the value of R is equal to 0. So the variable X and Y are not correlated. Again in figure number 4, we can draw a perfect straight line for all the data points of X and Y, and you will get R as -1. So again in this case we say that X and Y are strongly correlated, but the relation is inverse. So what I wanted to convey here is that correlation coefficient or correlation is one of the criteria for ranking the data, so that we can categorize where we get strong correlation, where we get moderate correlation, and where we get weak correlation, and where we get no correlation. Similarly, there are some other set of data. If you have any question, you can unmute yourself and ask, because in the screen sharing mode, I cannot see the comments in the chat box. Okay, so in case of information theoretic criteria, you can see here Hx is one variable and its corresponding circle is there. So it's a data set, we can say. Again, Hy is another data set, and there is some overlapping area you can see. So based on how much area is overlapped, that will decide the ranking criteria. For example, if we get two different circles, then you will say there is no correlation. If we get a very partial overlapping, then we say there is a light correlation. If we say that majority of the area is overlapping, then in that case we are saying, yeah, there is strong correlation, right? So these are the two approaches can be used for ranking the data. One is a correlation and one is information theoretic criteria. And in second class, that is information theoretic criteria, there could be so many parameters that you can consider in order to rank the data. Now all these things are very essential for constructing a decision tree. So briefly we will try to understand what is decision tree. And Then we will start understanding its mathematics. So, first important thing is that decision tree is a supervised machine learning, and we know that supervised machine learning, we have labeled the data, so we know input and its corresponding output. For example, we have a set of images of, let's say, dog, and its name will be there. So image and corresponding name is there, so labeled data is there. Again, a set of images of cat will be there and its label will be there, so label data would be there. And for dog images, you will train that if we get this image means it would be a dog. Similarly, for every image of cat, we train the data set for the cat. And then once your machine learning model will be ready, then you will provide an unknown image. And based on that unknown image, the machine learning model will tell you either it is a dog, or it is a cat, or it is something else. So this is how a supervised machine learning model will work. Now decision tree is a type of supervised machine learning where the data is continuously split according to certain parameters. So this part is very interesting. We split the data based on certain parameters. The tree, so when we say a tree, so we can say there will be leaf, there would be node, there would be root, and so many things, right? So here when we talk about decision tree, so two important entities are there. One is a decision nodes and leaves. So leaves are the decision or final outcomes, and the decision nodes are where the data is split. For example, you can see first node is denoted in the circle. Again, just like branches of the tree, there are two branches, and those are used to represent the internal nodes. Again, these internal nodes has two branches again, and you can see the final decisions or outcomes as a leaf. So this is a typical way of presenting a decision tree. But this is a theoretical part. So if we take one example so that you will come to know how decision tree is used to make certain decisions or to draw some conclusion. So you can see the important question in this example is we want to know if a person is fit or not. Now we started the tree with the age of that person. If the person is of age below 30, or if the person is having age greater than 30. So if age of the person is below 30, and if he eat a lot of pizza, then we can say that he may be unfit. Or other possibilities also there. The age of the person is below 30, and the age is he also don't eat a lot of pizza, then we can say that he fit. On other hand, if the age of a person is greater than 30, but he do exercise in the morning, then based on this we can make a final outcome that the person could be fit. The other probability is also there. Age is greater than 30, also that person don't do exercise, so we can say that he may be unfit. So this is how we identify certain criteria. Based on that criteria, we draw different branches just like a tree. And at the end, there will be a leaf to make certain decision. In this case, the decision is whether the person is fit for a given task or not. So this is a typical example of fall tree. But in this particular example, you may ask, sir, my age is below 30, I also eat a lot of pizza, but I'm perfectly fit. You may claim, right? So that possibility is there. So the question comes is that on which basis we should make branches, because there should be some valuable data. Based on that we should make a branches to decide whether that person is fit or unfit, and that mathematics we will try to understand in this particular lecture. So in order to understand whether to go for a branch or not, or what should be the parameter to decide the branches should be there or not, so two important parameters, one is entropy and second one is information gain based on entropy. And based on the value of entropy as well as information gain, we can decide the best way to split the tree, or it can also be used whether the splitting is possible or not. The information gain, like Guinea impurity, is a metric used to train the decision trees. Specifically, these metric measure the quality of a split. Right. So we will take one example and we will try to understand. Right. And this particular example I will be also taking after 2 3 slides as well. So try to understand this particular example. So here you can see the data set having values x and y, they are plotted on their corresponding axis, and you can see that there are 5 blue dots and 5 green dots, so that we can see here. Now what will happen if we draw a vertical line, or if we split the data set when x is equal to 0.5, right? Initially 10 data points, 5 blue, 5 green. Now we decided to draw a vertical line to split the data. Now when you split the data, what you can see, on left branch there are 4 blue dots are there, and on right side you will see one blue and 5 green colored dots. So this is how we divide the data set into two branches. And the question comes, whatever split we made, whether it is optimal or not. If it is optimal, then how we can say it is optimal? If we say it is not optimal, then what is the basis to say it is not optimal? So for that we need to quantify certain things, so that that value will help us to decide the splitting is correct or not, or that branching process is correct or not. And in this particular simple example you can easily understand, because only 10 points are there, that this particular split is not perfect. And if we want to make it perfect, if we draw a vertical line, or if we divide the data when x is equal to 2, then it is perfect. Why? Because on one branch you will get all blue colored dots, and on right branch you will see all green colored dots. So this is very easy to understand, but if we have thousands of data, then in that case it is very difficult for you to make a decision whether it is a perfect split or imperfect split, or what kind of split it is. So we need to quantify that, and in order to quantify that, the term entropy and information gain will help a lot. So again, after 2 slides we will come back to this example only. Before that we will try to understand entropy and the information gain. So, in the context of training decision trees, entropy can be roughly thought of as how much variance the data has. When we say variance means we talk about the spread of the data or different set of data. For example, in first example, you can say that a data set has only blue dots. You can see here only blue dots are there. So there is little variation because only one type of dot is there. So in this case, we say that there is low entropy because variation is not there. However, in second example, where a data set consists of blue dots, green dots, and red dots, so there is a variety. So three types of data is there, or variety of data is there. And here we can say that the entropy is very high, because when we express the first example in terms of probability, then we say that if we randomly pick a dot, then there are four blue dot and there are total four dots. So probability of getting the dot blue as 4 by 4, which is equal to 1. However, in second example, there are two blue color dots, two green dots, and two red dots. So probability of getting blue dot is 2 by 6. Same probability for green color dot, and same is the case for red color dot. So the probability of getting either blue or green or red dot is 1 by 3. So when we compare these two values, then we can say that the entropy is lower in first example because the variation is less. However, in second example, there is a lot of variation, so entropy at higher end. Now the question comes, how to calculate entropy mathematically when there are C classes. So class means in this example two blue dots, two green dots, and two red dots. So each color is nothing but a class. So if there are C number of classes, then the entropy is calculated by using this formula. E is equal to minus summation I is equal to 1 to C pi log to the base 2 pi, where pi is the probability of randomly picking an element of the class I, right? So by using this formula, we can calculate the entropy, right? And based on the value of that entropy, we can make a decision whether there is some information gain is there. So in order to understand how this particular mathematics is used to calculate the value of entropy, so we will take one example. Consider a data set of one blue dot, two green dot, and three red dots. So total six dots are there. So this information is given to us, and the formula that we discussed to estimate the entropy, so we are just using that formula. So the first part is the entropy for blue color dot, the entropy for green color dot, and the entropy for red color dot. So this is how we written the formula. So you can see here the the rounded part is related to entropy for blue color dot. Second circled part is related to green colored entropy, and third is related to red color. Now we know that there are total six dot, and out of that six only one dot is of blue color. So probability of getting blue color dot is 1 by 6. Again there are two green colored dot, so probability of getting green color dot is 2 by 6. And similarly there are three red colored dots, So probability of getting red color dot is 3 by 6. Now we can put all these values in this equation, and if we simplify, you will get the entropy for this example as 1.46. So sum of entropy of blue color dots, green color dots and red color dot is total entropy 1.46. So this is one example through which we will come to know when a data set is there, then how you can calculate the entropy for the same. We will take one simple example. Consider a data set consists of three dots and all dots are blue colored. So the total entropy would be 0. Why? Because total number of dots are 3 and all three dots are of blue color. So the probability of getting blue color dot is 3 by 3, 1. And when we put that value in this equation, you will get entropy as 0. So what we understood from this, if the value of it, yes,
Your presentation is not visible.
presentation, okay, just a minute. So how long it is not visible?
Uh, After 2 minutes.
2 minutes, okay, I will share once again. Can you see it now?
Yes, sir. Now it is visible.
Okay, and just a minute. Okay, did you understand this particular part?
Yes, sir.
Okay, so I will go ahead now to next slide. Yeah. Okay, so for example number one, where three types of data sets were there, we understood how to calculate the entropy. And in second example, where three dots were there, and all dots were of blue color. So probability of getting blue color dot is 1. So when you put that 1 in this equation, you will get entropy equal to 0. So what we understood from this, if there is a little variation in the data or no variation in the data, entropy is 0 or close to 0. However, as the variation increases, in first example, you will get larger value of entropy. So this particular part you need to understand, that less variation, entropy value is close to 0, large variation, large value of entropy. Now we again go back to our previous problem. So you can see here you can see 5 blue dots and 5 green dots, and now we will try to understand the significance of entropy value and information gain for this particular example. So when initially when there is no split, just like this particular graph as it is, then what we have 5 blue dots and 5 green dots. So total dots equal to 10. So probability of getting blue dot is 5 by 10, and probability of getting green dot is again 5 by 10. So that we can understand. So the entropy for this particular situation is calculated by using this formula as 1. Formula is there. Put these values into this equation and you will get entropy as 1. Now we will go to second case, where what we did, we drawn one vertical line when x is equal to 1.5. Now for this particular split, when we have two branches, left branch and right branch, we will try to estimate the entropy. So for left branch, you can see there are 4 dots and all dots are of blue color. So its corresponding entropy will be 0, because all dots are of same color. Now when we talk about the right side branch, then there is one blue colored dot and five green colored dot. So here you can calculate the entropy. So for one blue color dot you can calculate the its entropy, and for five green color dots you can calculate its entropy. So for right side branch you will get entropy as 0.65, whereas we already estimated for left side entropy as 0. So the total entropy, how to calculate, because for left side entropy is 0, for right side the entropy is 0.65. But on left branch there are 4 data points and on right branch there are 6 data points. So we need to estimate some weight, right? Directly we cannot sum both the sides. So as there are 4 data points on the left branch and 6 data points on the right branch, so weight of the left branch can be considered as zero point 0.4 and weight of the right branch can be taken as zero point 0.6. So the total entropy of the split is zero point 0.4 multiplied by 0 plus zero point 0.6 multiplied by 0.65. Why? Because the entropy of the left branch is, just a minute, I will draw once again, 1 2 3 4 and this is 5 and 1 2 3 4 5, let's say. Okay, so on left branch there are 4 data points, so entropy is 0 and its weight is zero point 0.4 because there are only 4 data points, so zero point 0.4 into 0. Whereas on right branch the entropy is zero point 0.6 and as there are 6 data points so weight is zero point 0.6. So multiplied those and upon simplification you will get the entropy for the split data set is 0.39. So this is how you can calculate the value of entropy. So when there was no split, all 10 data points were there, the entropy was 1. And now when the data is split into two parts, right branch and left branch, so you got entropy as 0.39. So whatever information we receive from the entropy value, that is called as information gain. So information gain is nothing but how much entropy we removed. So initially the value was higher, so a lot of entropy was there, and after splitting we lowered the value of entropy. So we removed some entropy and we get the gain as 0.61 because previously the entropy was 1, so a lot of entropy was there, and after split we reduce that value, so 1 minus 0.39, answer is 0.61. So this is how you can split the data and based on the value of entropy you can get the information gain. So what we can get from this example, to get higher information gain we should remove more and more entropy. So lower the value of entropy, higher the value of gain, and vice versa. So in the perfect case, each branch would contain only one color after the split, which means zero entropy. So again we will go to the same example. 1 2 3 4 5, 5 data points, and on right side let's say 5 data points, 1, 2, 3, 4, 5. And suppose if we draw a vertical line here, then for this left branch, as all dots having same color, so entropy would be 0. Similarly for the right branch, as all the dots having same color, so entropy is 0. So if we again assign some kind of weight, it doesn't change its value, right? So zero point 0.5 into 0 plus zero point 0.5 into 0, again answer is same. So entropy would be 0. So what we can say that if we draw vertical line here, then we can divide the data points into two different segments, and you will get 0 entropy means you will get more information, right? Because the value of entropy is close to 0 means maximum gain of information, because we clearly dividing the data points into two different segments, understandable segments. Again, these are some other observations, that is a set of only one class, let's say only blue color dots are there. It is extremely predictable because only blue color dots are there. So pick any randomly dot from it, it would be a blue color. So this would have low entropy, close to 0. Now, if there are a lot of data points, then in this case, the prediction is very difficult because of variation in the data is there. So this would have high entropy. So it would be definitely greater than 0 and far away from the 0. And we already saw the formula that we used to calculate the entropy. And the entropy information gain is calculated by just subtracting the weighted entropies of each branch from the original entropy. When training a decision tree using this matrix, the best split is chosen by the maximizing the information gain. So this particular statement is very important. If we have maximum information gain, definitely we should go for the split. If this information gain is very low, then there is no point in going for the branch, right? So again we will go back to our example and we will discuss once again. Okay, so here in this example what we discuss, how this tree is constructed based on so much data points, and for that data points we split the data or we created some branches. So eating a lot of pizza is one branch, exercise in the morning is another branch. Similarly, fit and unfit, these are the two criterias. So there should be a logical way to make a final decision. For example, you may say that I eat a lot of pizza but still I am very fit. Or somebody may say that I don't eat pizza ever but still I am unfit. So that probability is also there. So in order to make certain decisions or prepare a tree, what is very important? The value of entropy and corresponding information gain. So this value of entropy and information gain based on a lot of data set will be a criteria to split the data into two branches or constructing the decision tree. So that's it from my side. If you have any question related to decision tree, entropy, or information gain, the session is open for discussion.